All right, thank you, Jared. My name is Tim Phillips. I'm a research fellow here at the University of Texas, working under the direction of Joe Beeman. Today, I'm going to be talking about some of the work we've been doing with material and application development for laser powder bed fusion. So the first application I want to talk about is additive manufacturing of lithium-ion batteries. So we've been able to use laser powder bed fusion to additively manufacture high-performance battery anodes and cathodes. Now, in your traditional lithium-ion battery, you have an anode and a cathode, collectively known as your electrodes, and they're quite thin. They're about 100 microns thick, or the thickness of a sheet of paper. So to give them structural integrity, they're mounted on some foils, so an aluminum foil or a copper foil. And to get the final battery cell, you would stack these with a separator between them, and then you wind it, fold it, or stack it to build up the large battery cells that you're familiar with. Now, the challenge is that those current collectors, those foils that we use there, take up a lot of space in that final battery, but they don't add anything to the actual capacity of the battery. So what we've been able to do is remove those current collectors and instead use carbon fibers within our material matrix to build up much thicker electrodes that still have high performance. And when we do this, we're using additive manufacturing to build these, so we can take advantage of the geometric freedom that AM affords us and make conformal battery electrodes. So imagine working on a device, and instead of picking a battery out of a catalog, you can actually design a battery, both the geometry of it and the capacity of it, that meets your specific needs. Another application we're working on is additive manufacturing of pharmaceuticals. So to do this, we take a pharmaceutical drug and mix it with an edible polymer and use laser powder bed fusion to create personalized dosage forms. And when we do this, we're actually creating what's known as an amorphous solid dispersion, or ASD. What that means is that when we process this material with a laser, we melt the polymer, and the crystalline drug actually dissolves into that liquid polymer and gets locked in its amorphous state. And the amorphous state of this drug has orders of magnitude higher water solubility than the normal crystalline state. And so that means it has much more availability within your body, and it's a higher performance drug. So using additive manufacturing here, we're not only able to just create personalized dosage forms that are tailored to individuals, we're also able to create a product that has higher performance than if we took those same base materials and just put them in a pill. Another aspect of what we work on in our lab is developing advanced control methods for laser powder bed fusion. So to do that, we've created a custom open hardware or open platform SLS system. You see that here on the left. And I want to talk about one of the applications we've used this on, which involves our high-speed thermal camera. So during a build, we'll use our high-speed thermal camera to monitor the build conditions, and then we'll later identify correlations between what we can measure with our camera and our final part properties. So in the study in the middle, we're looking at the temperature that we measure with our camera and comparing that on the y-axis with the ultimate flexural strength of some parts that we were building. You see that there's a pretty big range here in the temperatures that we achieve, and that results in a pretty big range in the strength of these parts. And so we've taken that information and built a controller around that that can control our laser power to produce a much narrower range of these temperatures. And that's the blue data shown in the middle graph. And that results in a narrowing of our standard deviation of flexural strength as well. So using this method, we're able to create much more repeatable and much more uniform parts. We've taken that concept and expanded it into metal additive manufacturing as well. So here we're using some physics-based modeling and machine learning to predict optimal processing control parameters, and using those machine learning models to assess performance in situ during our building process. The images here are the results from one of our studies where we were trying to control the melt depth while we're building a certain feature here. On the left side is what we would expect to see if we didn't have this intelligent control process. So the red information, pull up my laser pointer. All right, this red information here is showing the melt that's created by the laser. And the profile of that is seen on the image below. You see it's got a lot of variation here, where the black line on this bottom graph was our target melt depth. So there's a lot of error between what the system's doing and what we wanted it to do. But when we use our physics-informed controller, we get the results on the right. And on the bottom here, that green line is now our melt profile. You see there's really good agreement between that profile and our target melt depth. So again, using this process, we're able to have much more control over the outcome of these parts. So those are just a few of the projects that we're working on in our lab. I have a poster at the back with more details on the additive manufacturing of lithium-ion batteries, and I'm happy to take any questions.